Video 6 in Chapter G here. We're going to be discussing more applied problems, if you will. Not really anything theoretical, nothing we'll have to prove necessarily. So I think you will enjoy this video. And what we're going to talk about in this section is the relationship that the angles of a triangle have with their respective sides. And so if we look at this example here that's on your notes, we can see that the longest side of this triangle is, let's see, that would be side BC here at 12.1 centimeters. And the medium side, the middle side, would be the 9.1, which is side AB. And the shortest side is the 7.5, which is side AC. And so if we were also to look at the largest, medium, and smallest angles, we'll start to notice a particular pattern. So the largest angle up here is angle A, which is 93 degrees. And the medium angle is angle C at 49, and our smallest angle is angle B at 38. Now, when I ask you to compare the longest side with its largest angle, do you perhaps notice the particular pattern that should be coming out at you? And that is that if you took the longest side, which is BC again, and you matched it up with the largest angle, notice that the largest side and largest angle are opposite of each other. And hopefully that makes sense. The wider this angle is, the wider the side opposite at the end of that angle must be. The shorter the angle, the smaller the angle, like this 38, then the smaller the side opposite of that angle. Okay? So the relationship that I want you to notice is that the longer the side, the larger the angle opposite of it. And the smaller the side, the smaller the angle opposite of it. And that leads us to Theorems 5.10 and 5.11, which can be read either way. One is basically the converse of the other. So Theorem 5.10 says if two sides of a triangle are not congruent, then the larger angle lies opposite the longer side. Okay? So it references the sides first, sides first, then it talks about the angles. And if we can flip it around and say, well, if we knew that one angle was bigger than the other, then the side opposite of that angle must be larger than the side opposite the smaller angle. So it can be read forwards or backwards. So if we were looking at an example and I wanted to know what are the angles from smallest to largest when I only know the side lengths? Well, we could use the law of sines and cosines and actually figure out what these angles are, but we don't really need to do that. The smallest angle up here would be opposite the smallest side, and the smallest side is the 4, so the angle opposite of that would be angle C. And then the largest side would be opposite the largest angle would be opposite the largest side, and if the largest side is 9, AC, then angle B must be the largest, which by the process of elimination leads us to angle A, which must be the medium angle. Do we specifically know how big these three angles are right now? No, but we definitely know that angle C is smaller than angle A is smaller than angle B. So we could turn it around and talk about the angles with the sides. Well, I know 58 is smaller than 62, but I wasn't given what the third angle was. Well, here's where you're just going to have to do a little bit of legwork. We know all three angles add up to be 180, so if we subtract away 58 and we subtract away 62, we're really subtracting away, what, 120 degrees, which leaves 60 degrees for angle T. So now we can discuss which side is the smallest, and so the smallest side would be opposite the smallest angle, which is the 58. So TV is the smallest, and then 60 is our middle number, so the side opposite of it is UV, which leads us to the largest side, which is opposite the 62 degree angle, the largest angle, which is UT. And that's it. We're done. Now, there's one other feature we need to talk about besides the relationship between angles and sides of a triangle, and that's exploring the lengths of a triangle. For example, I can't just randomly give you three numbers that supposedly represent side lengths of a triangle. Not every three numbers I give you are going to make a triangle. So here's what we're going to do for a short time with Sketchpad here, is to discuss what has to happen for the three sides of a triangle to really make a triangle. So if we look right now, I kind of disconnected, if you will, uh, vertex A here, okay? So you'll see these two A's, but really, if I connect them together, I've got a triangle, okay? So if I disconnect them, right now, I don't have a triangle. So if I look at these three side lengths, these three lengths would not produce a triangle, correct? Correct. So is there anything that needs to be special about either one of these two lengths to fully make a triangle? And you might go, well, one thing I notice is both of these are smaller than this side. Is that something special? Not necessarily. You know, I could take, let's say, this guy, make it larger than this side. Can I still make a triangle? Yeah, I'd have to shorten this piece up, and boom, we got a triangle. So there's nothing special individually about these two pieces to make a triangle. What we need to consider is what they can do together, okay? So if I were to add these two things together, I cannot make a triangle if it's a certain length, okay? So if we look right now, okay, this obviously is not making a triangle. This cannot work. And so you'll notice the sum of these two sides, AB and AC, are smaller than our largest side. And that's why we can't make a triangle. But if I were to connect together these two, now notice the length of both of them working together. They outweigh the largest side put together. And so if you really think about it, if we made these things get really, really small, and I try to make it about the smallest possible triangle I could here. No, not quite. Right in this vicinity. Notice that these two lengths, AB and AC, they're almost right on top of BC, but they're still just a little bit bigger, just by 4/100ths of a centimeter, compared to BC. Now, what happens if AB and AC are exactly the same as BC? Let's make that happen. Right there. So if these two lengths add up to be the same thing as the longest side, do we have a triangle anymore? And we don't. We really now have a segment that kind of has two smaller segments right on top of it. So here's what I want you to get out of this. The conclusion I want you guys to write is that the two shortest sides of a triangle, they can't do anything individually against the largest side, but you must add them together, and it must be greater than, strictly greater than, not greater than or equal to, the longest side. Okay? The two shortest sides of a triangle must add to be greater than the longest side. So let's look at some examples. Can we make a triangle out of lengths of 6, 10, and 3? Well, what a lot of people will do will automatically look at this and go, all right, well, these two added up, that's 16, that's greater than 3, so yeah, it works. But we need to look at the two shortest sides, which would be the 6 and the 3. Do they add up to be more than the largest side? The answer would be no. 9 is not greater than 10. So those three lengths, you know, if you were to cut popsicle sticks or, you know, something that had a length of 6, 3, and 10, you wouldn't be able to make a triangle out of those three things. And so what if we looked at lengths of 5, 10, and 5? Could we make a triangle out of that? And once again, this is where we would have to say technically no. This is where we would have, let me just make it out real quick, like let's say that's our 10, and then we'd have two 5s. Try to make those as close as possible to being about the same. The two 5s would have to sit right on top of the 10, and we would basically have a collapsed triangle. It would be the smallest non-existent triangle we could have. So again, it must be strictly greater than for it to work. If one of these sides was 5.01, then we'd have 10.01 for the sum, then it would work. It would almost look like it was a completely deflated triangle, but it wouldn't be. Now to the last type of problem. It says a triangle has sides 9 and 13. What lengths could the third side be? So what we're going to write is what's called a compound inequality, which basically tells us the smallest the third side could be all the way up to the largest the third side could be. Okay? So we could go and we could give lots of numbers. We could technically give infinitely many numbers. It doesn't have to be just a whole number. We could be talking about fractions or decimals as well. So here's what we need to consider. Let me write this out. There's really going to be two scenarios that are going to happen here. And so let's call the third side x. We don't know how big it is, so we'll call it x. Well, let's talk about the two smallest sides. We don't know how big x is, so we don't know if it's one of the two smallest sides, or what if it's the largest side. There's where our two scenarios are going to come into play. So let me just copy this real quick. For our two scenarios. Let's say x and the 9, it can't be the x and the 13, are the two smallest sides. So we're going to go with the assumption that the 13 is the longest side over here. And now let's say on this side that maybe x is the longest side. We don't know. It could happen. So what we're going to do is set up the inequality. We said that the sum of the two smaller sides, which would be the x and the 9, must be bigger than the longest side, which is the 13. Now we're going to solve this inequality like we would just a regular equality. Just pretend that greater than sign is really an equal sign. And we would subtract the 9 over, and we would say that x would have to be bigger than 4. So if x was bigger than 4, but not including 4, if x was 4.5, or if it was 5, or if it was 6, if it was 7, it would work out to make a triangle. But there's going to be a certain number x where it's no longer going to work. And that's what we're going to figure out over here. So again, we say, well, the two shortest sides, we're going to assume 9 and 13 are the two shortest, that they must add up to be longer than the longest side. And here we're going to say, what if x was the longest side? Well, 9 and 13 is 22, so there's real no algebra involved here. But the x side, if it was the longest, would have to be smaller than 22. So now we're going to combine these two inequalities into a single compound inequality. So we're going to say 4 is the smallest number, and x could be bigger than it, but it was restricted by and could not go over 22. So x, our unknown side, our third side, can be any value between, but not including, 4 and 22. And another term we could use to describe this, 4 and 22, would be to say that it is x is exclusively between 4 and 22, which means we have to exclude the specific values of 4 and 22. If I wanted to include 4 and 22 as possible values, I would call that x could inclusively be between 4 and 22. Now, the last problem I want you guys to do on your own, which is very similar to what we just did. And there's a little pattern that can be found, and I'm not going to point it out to you, but we will discuss it in class, of how you could easily figure out the two numbers that x, the third side, could be in between. And I want you to try to use this example that we just did. Think of the 4 and 22. How could you get those numbers very quickly? So I'm going to leave that to you guys to see if you can find the pattern, and we'll discuss about it the next day in class. That's all for video 6. Adios.